Today I'm going to find the output impedance in my signal generator, this piece of shit right here. I say that because it gives me these don't really look too sinusoidal. There's a bunch of blips in them, and this thing isn't too accurate with everything, and amplitude changes with the load and whatnot. But it's good enough for a little experiment here. So what I have on channel 1 is all I'm doing is probing the output terminals of the frequency generator. And what I'm going to do is change the load that is attached to it and see how the voltage changes with the load. And the way we get the output impedance from that is we know that we've previously defined for impedances here that if there's a voltage across it and a current entering inside of it, the impedance, or in this case we're talking about resistance, is defined as that voltage across it over the current entering it. And so when we're calculating the current that we're drawing here, notice that the sign is different of this current. So when we actually go to find our calculated impedance, we're going to have to take the opposite of the voltage over the current, just because we're defining the current leaving like that. So we'll see what we observe. I suspect we'll find something like this if the slope is, change in y over the change in x, where we have I and v here. We'll have something like this. If this is a log scale, it'll be linear like this. So, if resistance is really high, then by voltage division, if this is really low, we'll have most of that load, or the open circuit voltage here, appearing across this. But if the load is really tiny and approaching zero, most of the voltage in this loop will be dissipated over its internal impedance first. So what I have here is just a random assortment of resistors, 20K, 10K. I measured these beforehand and whatnot. And all I'm going to do is plot them in here. I already jotted down the resistance values I'm going to test. And I'll jot down the voltage measured, and I'll calculate the current as just the voltage over the resistance that I know. And we'll see what pops up on this graph here. And if you don't have a scope to measure your peak to peak, try to find a signal generator that outputs square waves, because then you know that the RMS value is the same as the peak. But, it doesn't really matter. You can always scale it later if you know what you're doing. So let's see what happens. So here are the results. It's definitely linear, and the axes do not need to be transformed into logarithmic scale. Here's just a Desmos example illustrating why it's linear off the bat. Here's just a pretend voltage division equation up in Y1, where 10 volt source and 10 ohm resistance, and we're changing the other bottom resistance X, and we see, okay, that gives us non-linearity. Current is just that voltage over some resistance that we're changing as well. It's non-linear, but it turns out if we divide one by the other, and plot it at every point as a different resistance value, then it gives us our linear slope here. So yeah, here all I'm doing is taking 11 different resistance values, pretty arbitrary, and plotting them in plotting the result of V versus I in the list. And these blue arrangements of dots is obviously linear. But back to the results, we see I got rid of some of these lower resistance values because they really skewed the results. Here's just a least squares regression trend line. If we take the equation it gave us, here's the slope, here's the inverse of the slope, and here's the negative of the inverse of the slope, and that's about 600 ohms for the internal impedance. And I actually found the spec sheet for the function generator I was using and measuring, and right on the inside, it was right here the whole time. 600 ohm output impedance. So it's pretty cool that we verified the correct impedance. And yeah, if you have any questions, let me know. Again, all we did was assume here's our internal impedance, we're changing the load and plotting different values for resistances. All right, thanks for watching.